Field crop diseases. Growers and professional applicators should be able to identify the major diseases of field crops and have a basic understanding of pathogen biology and life cycles. It's important for each party to recognize when a timely fungicide application might prove beneficial. It's equally important to avoid making unwarranted applications. The traditional disease pyramid illustrates the fundamental relationships between the four factors needed for an infectious disease to develop: a pathogenic organism capable of causing disease, a host plant susceptible to infection by the pathogen, a favorable environment for the pathogen, and time, both the specific point in time at which a particular event in the disease development occurs and the length of time during which the event takes place. Disease management practices remove one or more of the factors to reduce or eliminate the plant diseases. For example, planting disease-resistant varieties and hybrids removes the susceptible host plant, thus reducing the potential for disease development. Likewise, rotating crops and managing crop residues limits the potential for the disease by reducing pathogen populations. The usefulness of the traditional disease pyramid is limited because it does not account for pathogen reproduction, dispersal, and survival strategies. It's often beneficial to think about and develop disease management strategies based on the pathogen's life cycle. Where are the weak links in the disease cycle? Can a fungicide application be delayed until a threshold has been met? These factors are important in terms of proper application timing. An important aspect of the life cycle is whether or not it is monocyclic or polycyclic. Monocyclic disease pathogens complete one generation in a given growing season. An initial infection occurs, but for a variety of reasons, the resultant spores do not reinfect during the same growing season. Even though monocyclic pathogens complete one generation per year, they are capable of reaching epidemic levels and causing economic losses when given a favorable environment, susceptible host, sufficient inoculum, and time. Fusarium head blight and Sclerotinia stem rot of soybean are examples of monocyclic diseases. Polycyclic disease pathogens, including rust and many leaf blight pathogens, produce additional inoculum following infection that reinfect the crop during the same growing season. Given a favorable environment and sufficient time, many pathogens can complete multiple cycles per season. Does this mean that polycyclic diseases will always reach epidemic levels and cause economic loss? No. Many foliar diseases are polycyclic, yet even with a sufficient inoculum load and a susceptible variety, these diseases normally do not reach epidemic levels. Without favorable environmental conditions for sufficient duration, they are unlikely to reach epidemic levels. Disease pressure plays a critical role in the degree and consistency of yield response to a foliar fungicide application. Research trials at the University of Illinois have shown that if at least 15% of the ear leaf area was affected by a disease at the end of a season, a foliar fungicide applied between tasseling and silking probably would have been beneficial. The challenge is predicting the level of disease pressure likely to develop later in the season. We can use disease risk factors and disease observations collected just before tassel emergence to predict future disease severity and help decide whether to apply a foliar fungicide. How will a variety or hybrid respond to a specific pathogen? There are three categories of plant responses to pathogens: susceptible, tolerant, and resistant. A susceptible variety or hybrid has no defense mechanisms against the pathogen. Symptoms and yield loss can be severe. A tolerant variety also has no major defense mechanisms, but yield loss is less compared to a susceptible variety or hybrid. A resistant variety has defense mechanisms that limit the infection, pathogen, reproduction, or lesion size. Resistance is not always complete, and not all forms of resistance are equally effective, which is why modifiers such as highly resistant, moderately resistant, or slightly resistant are used. What crop was previously grown in the field? Many foliar pathogens, such as gray leaf spot or northern corn leaf blight, survive in corn residue. The risk of foliar diseases increases in continuous corn production systems, especially when the previous year's crop residues remain on the soil surface. Weather determines if the environment is favorable for the pathogen. In general, warm, rainy, and/or humid weather increases the risk for disease development. Does the field have a history of corn disease? Fields with previously high disease severity, fields in river bottoms or low areas, or those surrounded by trees may be more prone to foliar corn diseases, thus increasing their risk factor. Do your fields have any of these disease risk factors? Scouting observations should also be taken into account. Scout for foliar diseases in corn just before tassel emergence. Current disease management guidelines suggest applying foliar fungicides under the following conditions based on hybrid susceptibility. For susceptible hybrids, apply a foliar fungicide if disease symptoms are present on the third leaf below the ear or higher on 50% of the plants examined. In general, susceptible hybrids will have a greater yield response to a foliar fungicide, especially when disease pressure is high. For hybrids with intermediate resistance, consider applying a foliar fungicide if disease symptoms are present on the third leaf below the ear or higher on 50% of the plants examined. If the field is in an area with a history of foliar disease, if the previous crop was corn, if there is 35% or more surface residue, and if the weather is warm and humid. Foliar fungicide applications are generally not recommended for resistant hybrids. The yield response from a foliar fungicide on a resistant hybrid is not likely to recover the cost of the application. It's worth noting that the use of a disease-resistant variety or hybrid is often the simplest, cheapest, and most effective method of disease management. This section contains a small selection of field crop diseases that a commercial pesticide applicator might encounter and possibly treat. For each disease, you will find information relating to disease symptoms, signs, survival, spread, and management. Specific fungicide recommendations have been omitted because these recommendations are revised regularly and are available in pest newsletters, fact sheets, websites, or other publications from the University of Illinois Extension. Northern corn leaf spot mainly occurs on inbred lines used in seed production. The disease is rarely a problem on hybrids. Northern corn leaf spot has 5 distinct races that can cause different symptoms. Only race 3 is important in Illinois. Race 3 symptoms resemble a string of pearls where multiple small circular lesions develop closely together. Symptoms of this disease are sometimes confused with northern corn leaf blight, southern corn leaf blight, and anthracnose. The northern corn leaf spot pathogen overwinters on corn residue. Infections occur between silking and maturity. Warm, damp weather promotes the development of this polycyclic disease. When possible, plant hybrids that are resistant to northern corn leaf spot. Managing residues by rotating crops and tilling to reduce corn debris decreases inoculum and therefore the risk of disease. Foliar fungicides may be necessary to manage this disease on inbred lines and in hybrid seed corn production. Yield loss may occur if the lower 3 leaves are infected before tasseling or up to 2 weeks after tasseling. Northern corn leaf blight. Northern corn leaf blight lesions appear on the lower leaves first. The length or size of the lesions may vary with their different reactions to resistance genes within the corn hybrids. They are long, elliptical, and often described as being cigar-shaped. The lesions range from a grayish-green to tan in color. Northern corn leaf blight is prevalent wherever corn is grown. The northern corn leaf blight pathogen overwinters on infected corn residue. Wind and splashing water disperse the spores to the corn plants. Infections generally take place during or after silking. Moderate temperatures and heavy dews promote the development of this polycyclic disease. Resistant hybrids are the most effective means of controlling northern corn leaf blight. Decrease overwintering inoculum by managing crop residues and rotating crops. Scout susceptible inbred corn lines in hybrid seed corn fields just prior to tassel emergence. Significant yield loss may occur if the lower 3 leaves are infected before tasseling to 2 weeks after tasseling. Foliar fungicides may be needed to prevent yield loss. Southern rust. Southern rust symptoms start as small, yellow spots that develop between the leaf veins. Infected areas then form small, circular to oval, and light cinnamon brown to orange pustules. Southern rust pustules are mainly scattered on the upper leaf surface. However, a few pustules may be seen on the lower leaf surface. Pustules may also appear on husks, ear shanks, stalks, and leaf sheaths. Southern rust's symptoms can be confused with those of common rust, a disease that is seldom a concern on hybrid corn. Several characteristics help distinguish southern rust from common rust. Southern rust's pustules are lighter in color and densely scattered over the upper leaf surface. Common rust has darker, cinnamon brown to red pustules scattered on both leaf surfaces. Southern rust does not overwinter in the corn belt. The disease is often present in the southwestern United States, but occasionally spreads to the corn belt as the pathogen spores blow in from the southern U.S. and Mexico. The disease is most likely to appear after silking and is favored by warm temperatures and high relative humidity. Southern rust can be a serious problem on both inbred and hybrid corn. Fungicides can be most beneficial if applied early and when there are few pustules on the leaves. Southern rust observations are tracked on the Corn Pest Information Platform for Extension and Education. This tracking tool can help decide whether or not to apply a foliar fungicide. Soybean rust. Soybean rust can occur at any growth stage, but symptoms commonly appear after flowering. Small necrotic spots usually develop first on the undersides of the leaves. Tiny, raised, gray, tan, or brown pustules then form on the undersides of the leaves. Pustules rupture and release spores which have a sugar crystal-like appearance. Soybean rust does not overwinter in the Midwest. The pathogen spores are wind-blown from southern states. Northward movement depends on the dispersal of spores and disease establishment in new areas. Infections can occur at all stages of soybean development, but are most common after flowering. Soybean rust is favored by extended periods of cool, wet weather and high humidity. Foliar fungicides are used extensively to manage soybean rust in areas of the southern U.S. and countries where the disease occurs regularly. Soybean rust detections in Illinois have occurred late in the season when soybean plants were nearing maturity and no yield loss had occurred. Track soybean rust observations and progression on the Soybean Pest Information Platform for Extension and Education. Many terms are used to describe the mobility of fungicides. Examples include contact, protective contact, local penetrant, local systemic, translocated, eradicant, and curative. Protective contact fungicides do not enter the plant, but rather remain on the surface of the foliage, protecting it from infection for some period of time. As with any pesticide, rainfall or irrigation within a few hours after application washes away much of the pesticide and greatly reduces the protective value. Even after drying on the plant surface, residues continue to be eroded via rain, dew, vaporization, and sunlight, thus reducing the protection. Furthermore, as plant tissues expand or are replaced, the new tissue is left unprotected. For these reasons, protective contact fungicides need to be reapplied more often than systemic fungicides. Local penetrant fungicides, sometimes called local systemics, are absorbed in the immediate area of application but are not translocated far from the site of uptake. They serve to prevent the development of disease at or near the site of uptake. Systemic fungicides are more mobile than local penetrants. However, nearly all systemic fungicides on the market move only upward in the plant. The terms curative and eradicant are sometimes used to further describe certain systemic and local penetrant fungicides. These terms indicate that the fungicide has the ability to stop the progress of infections that may have occurred a few hours or days before the application. Each year, extension plant pathologists from across the United States work within committees to develop fungicide efficacy ratings for various crops. The efficacy ratings are determined by field testing the materials over multiple years and locations. Efficacy is based on the proper application timing and overall level of disease in the field at the time of application. These tables include marketed products that have been tested by the committees. Tables are not intended to be lists of all labeled products. Pesticide-resistant pests develop as a consequence of repeatedly using products with the same site of action to kill specific pests not controlled in any other manner. Specific recommendations for reducing the potential for fungicide resistance development include the following. The use of fungicides should be integrated into an overall disease and pest management program that includes appropriate cultural practices, host plant resistance, and scouting. Apply fungicides when disease symptoms first appear or when predictive models suggest the disease is likely to occur. Do not use a lower than recommended rate or rely upon curative or late applications. Avoid using an active ingredient or members of the same frac group more than once per season. If multiple applications are necessary, alternate or tank mix effective active ingredients from different frac groups. Monitor the efficacy of all fungicides used and record other factors that may influence fungicide performance and/or disease development. If you suspect fungicide resistance, contact a manufacturer representative, local extension specialist, or certified crop advisor for further investigation.
In this module, we'll take a deep dive into the world of spray nozzles, looking specifically to optimize droplet size based on application requirements. Then we'll dig into some common, helpful ancillary technology. Finally, we'll expand on the mixing and calibration math introduced in general standards and try to apply that to field crop scenarios. All equations shown in yellow throughout this module are available on the equation sheet, which can be found in the Additional Resources section of this training. An identical copy of that equation sheet is provided for use when taking the field crops exam. Additionally, the use of a calculator and scratch paper in this section and on the exam is encouraged, but not required. It is important to understand that nozzle choice is primarily based upon specific pesticide application requirements, rather than the sprayer they're used on. Because of the many types of products used, diverse pests being targeted, and crop-specific challenges, there isn't a single nozzle that is best for all occasions. Here are the basic characteristics that will distinguish one nozzle from another. The first is the orifice size, which meters the flow rate through the nozzle. We'll discuss later how the required nozzle flow rate can be calculated for a prescribed spray application rate. The next characteristic is the uniformity of spray. The design of the nozzle and fan angle of the spray pattern will play a role here. The main driver, though, in nozzle selection is droplet size, which dictates how thoroughly the target is covered with spray, as well as the potential for off-target spray drift. Selecting and controlling droplet size is the primary mechanism for meeting our two main goals of pesticide application. Number one, to effectively control the target pest, and number two, to mitigate drift potential. Droplet size is the measure of a droplet's diameter in microns, or micrometers, wherein 1 micron is roughly 1/25,000th of an inch, and 100 microns is roughly the diameter of a human hair. Spray droplets are measured using laser diffraction or calibrated photography. It is generally accepted that droplets with a diameter of 150 microns or less are at higher risk of drift. Not that larger droplets don't drift, but that this is the threshold below which drift potential increases very quickly. To illustrate the reason why 150 microns is used as a threshold, consider this study done by the Ohio State University Extension several years back. Individual droplets of a controlled diameter were released at a height of 18 inches into a 6 mile per hour wind. As you can see, the 100 micron droplet moves significantly further than the 200 or 150 micron droplet. For the purposes of reducing drift in agricultural applications, it's generally desirable to minimize the creation of droplets smaller than 150 microns, regardless of the requirements for coverage. Boom height also has an effect on the distance spray droplets move off target when subjected to winds. Consider this study where droplets of various sizes were released from several heights into a 10-mile-per-hour crosswind. There's not much effect on the 300 micron droplets. However, as we look at smaller droplets, the drift distance can become considerable. This data was also part of what established 150 microns as our cutoff for driftable fine droplets. In general, a spray height of 24 to 30 inches is recommended, and thus we must strive to reduce the creation of droplets smaller than 150 microns. Since we know that a nozzle produces a range of droplet sizes, the question becomes, how do we compare the droplet spectrum of one nozzle to the droplet spectrum of another nozzle? The droplet spectrum of a nozzle generally takes the form of a bell-shaped curve, like you see here, when arranging droplets from the smallest to the largest. The majority of the spray volume is in the middle of the curve, centered on the volume median diameter, or VMD. This is the droplet size in microns at which half of the spray volume is in smaller droplets and half is in larger droplets. For example, if 1 gallon of spray was put through a nozzle that claimed to have a VMD of 425 microns, half that gallon would come out in droplets smaller than 425 microns, and the other half gallon would come out in droplets larger than 425 microns. Nozzles are often compared by VMD when assessing the need for spray coverage. Another way of classifying the droplet spectrum is by the relative risk of drift. Since we define droplets smaller than 150 microns as at high risk of drift, we can look at what percent volume is less than 150 microns, or what percent of every gallon of spray is less than 150 microns. In comparing nozzles, a higher percent less than 150 means higher potential for spray drift. To summarize droplet spectrum classification, ASABE has established standardized droplet spectrum categories. These are used not only by nozzle manufacturers, but by pesticide labels when prescribing allowable droplet sizing. Essentially, several named categories, as seen here, correspond to discrete ranges of volume median diameter. For example, the nozzle described earlier with a VMD of 425 microns would be categorized as a very coarse, or VC droplet spectrum, since its VMD falls between 404 and 502 microns. These categories also have color codes to make nozzle catalogs easier to navigate. We've talked about nozzle characteristics in general, but it's also worthwhile to discuss how everything affects droplet size. The 4 highlighted items here are listed in order of influence to droplet size. The overall design of the nozzle has the biggest impact, and we'll look at some common example designs which illustrate this. Nozzle orifice size was discussed earlier for its effect on flow rate. It will also directly impact droplet size, such that smaller orifices will create smaller droplets. Pressure is another factor in droplet size. You can think of higher pressures being equivalent to higher drift potential, since higher pressures at the nozzle will create smaller droplets. The potential for spray drift can be reduced by using pressures at the low end of the nozzle manufacturer's recommended range. The nozzle fan angle plays a lesser role in droplet size. Wider fan angles will create smaller droplets. Although it's true that using narrower fan angles will create larger droplets and reduce drift potential, narrower fan angle nozzles generally require greater boom height to maintain proper overlap, which usually negates any advantage in reducing drift. With all these things in mind, let's look at some nozzle designs. The first 3 nozzles we'll look at are a bit special, in that they're available in very large orifice sizes. Liquid fertilizer applications require much higher spray application rates than other applications, and these nozzles will fit that bill, although they can still be found in scaled down sizes for other applications. The first nozzle in this group is the flooding nozzle. This nozzle is characterized by a very wide angle spray pattern. It's also very pressure sensitive. That is, a small amount of change in pressure will have a large effect on droplet size and uniformity. Physically, these are very simple nozzles. The spray is metered through the orifice of the nozzle, and as it exits the orifice, it hits the deflector plate, which redirects the spray to form a wide fan pattern. Because of the issues with uniformity, these nozzles require 100% overlap with neighboring nozzles. Here is a flooding nozzle in action. Notice the heavier band of spray at the edges of the fan. Also note the wide range of droplet sizes produced. The gray clouds are small droplets. Because flooding nozzles are so pressure sensitive, special care must be taken to maintain operating pressure. The turbo flood nozzle is an adaptation of the original flooding nozzle, designed to improve uniformity, reduce pressure sensitivity, and reduce drift potential. There are two design features which make this possible. First, the inclusion of a pre-orifice. Looking at the cutaway at the top left, the inlet side of the nozzle is at the left and the outlet is at the bottom. A pre-orifice is an inlet orifice, shown in black in the cutaway, which is smaller than the exit orifice. This creates a pressure drop within the nozzle, reducing pressure at the exit orifice, and ultimately resulting in larger droplets. The second design feature is the turbulence chamber. In the cutaway, this is the void area to the right of the exit orifice. The turbulence chamber magnifies the effect of the pre-orifice and is where the turbo part of the nozzle name comes from. Neither of these design features are unique to this nozzle, but it was one of the first to incorporate them. Because of the improved uniformity, turbo flood nozzles only require 50% overlap, as opposed to the 100% required for standard floating nozzles. This allows for the use of wider spacing on booms. Here we see the turbo flood nozzle in action. There are two big differences between this and the original flooding nozzle we saw earlier. First, there are no longer any heavy bands of spray at the edges of the pattern. Second, the amount of small droplets being formed is greatly reduced, as there are hardly any gray cloudy areas. The last of our three high flow rate nozzles is appropriately, and not so originally called, the high flow nozzle. This is a more recent design which also sought to go one step further than the turbo flood nozzle in reducing drift. The high flow nozzle is characterized by a 140-degree fan angle spray pattern and creates an extremely coarse to ultra coarse droplet spectrum, regardless of orifice size. In addition to the low drift potential, the high flow nozzle is also capable of being operated within a much wider pressure range than turbo flood nozzles. This is particularly important for sprayers equipped with systems to dynamically change pressure, such as rate controllers, which will be discussed a little later. Having looked at the three high flow nozzles, we'll now look at more commonly used nozzles for standard rate applications. The first nozzle is the extended range flat fan. The extended range part of the title is referring to the pressure operating range, which is wider than the standard flat fan nozzles which came before it. Now though, even though this nozzle is considered the standard flat fan, it's still called the extended range. If you look at the cutaway diagram at the right, you'll see that this nozzle is about as basic as it gets. The exit orifice at the bottom both meters the spray and forms the spray pattern through an eyelet-shaped orifice. Looking down at the droplet spectrum category chart, the first column contains the nozzle info. For example, let's look at the red XR8004. The XR stands for extended range, the 80 stands for 80-degree fan angle, and the 04 stands for the orifice size. The red background in the box indicates that the nozzle tip color is red. Don't worry, none of the color coding is on the exam. The rest of the chart shows the droplet spectrum category for each orifice size under given pressures. For this nozzle, we can see that under most conditions, we'll have either a medium or a fine droplet size spectrum. This nozzle can be a good choice when coverage is essential, but there will be significant risk of drift. Here's a look at an extended range nozzle in action. This is a 110-degree variant with an 04 orifice. Notice the large amount of gray clouds of fine droplets being created, and keep this image in mind as we move on to look at nozzles which are designed to reduce drift potential. The pre-orifice flat fan nozzle modifies the extended range nozzle by installing a pre-orifice. As previously discussed, the pre-orifice will create a pressure drop within the nozzle and reduce the amount of fine droplets created. Looking at the chart at the bottom, we can see that this nozzle will produce a coarse to medium droplet spectrum. Essentially, every company that makes nozzles for sprayers has their version of the pre-orifice nozzle. TJet has the Drift Guard, or DG, Hypro has the Guardian nozzle, Wilger has come out with a range of pre-orifice nozzles which provide various ratios of pre-orifice size to exit orifice size in order to provide different levels of drift reduction. Here is the T-Jet drift guard nozzle in action. This is a 110-degree variant in the 04 orifice size. Notice the reduction in gray clouds, indicating the drift potential is being reduced. The turbo flat fan nozzle is designed similar to the turbo flood nozzle, but it has a very wide pressure operating range. This nozzle is often sought out by folks looking for a jack of all trades, since many different droplet spectrums, from very coarse to fine, can be had with a single spray tip, simply by adjusting pressure. This could also be considered a weakness, however, as pressure must be kept very consistent to maintain the desired droplet spectrum. Here is the turbo flat fan in action. This is a 110-degree variant in the 04 orifice size. The spray pattern should look similar to the pre-orifice nozzle we just looked at, since it's putting out the same droplet spectrum category. The main difference with this nozzle is that a small change in pressure would make a relatively larger change in droplet size. Air induction nozzles are the most complex designs on the market, but also offer the widest pressure operating ranges and lowest potential for drift. These nozzles are designed to induce ambient air into the fluid flow via Venturi action. This incorporates air bubbles into the spray droplets, making them larger. There are a wide variety of air induction nozzle variations, and while all of them have relatively large droplet spectrums, they each seek to fill one specific niche or another. Here is one air induction nozzle in action. This is a 110-degree variant turbo air induction nozzle with an 04 orifice. Air induction nozzles create very few fine droplets, and have become the standard for many herbicide applications, where drift can be the most damaging. To get some perspective on the differences between the nozzles we've discussed, consider this comparison. The chart represents the percent less than 150 microns at 40 psi. So, the larger the number, the greater the risk of drift. For the extended range nozzle, nearly 1/3 of every gallon of spray is at high risk of drift. In comparison, turbo flat fan nozzles cut this down to 13%. Moving down to the turbo air induction nozzle that we just looked at, the risk of drift is cut down dramatically. In an ideal world, we would always use the nozzle with the lowest potential for drift. Unfortunately, the trade-off is that using larger droplet sizes will also reduce coverage and efficacy of the pesticide product. Another variation of nozzle to be familiar with is the twin spray configuration. There are a wide variety of designs which allow one nozzle position on a spray bim to be used for multiple orifices. All twin spray designs are targeted to increase canopy penetration by introducing multiple angles of attack for the spray. There is, however, a potential downside. Splitting the amount of spray from one nozzle position into two orifices means using two orifices which are usually half the size of what the single orifice would be. As we discussed earlier, smaller orifices produce smaller droplets and a greater potential for drift. Air induction nozzles are affected in this way as well, but to a much lesser extent than non-air induction nozzles. Because of this, you'll find quite a wide array of air induction twin nozzles. When selecting a nozzle, the orifice or tip material is worthy of note. Nozzles are a high wear item, and the rate of wear depends on factors such as the nozzle tip material, spray formulation, and operating pressure. Looking specifically at the impact of nozzle tip material, consider the chart here, which shows the results of a 40-hour wear test on nozzles of various materials. In this test, wear was defined as the percent change in flow rate for a set pressure. The most wear-resistant nozzles were ceramic, thermoplastic, and hardened stainless steel. Consequently, most nozzles on the market use one of these materials. As nozzles wear, not only does the flow rate change, but the spray pattern changes as well. When nozzles get too worn, the spray pattern becomes too heavy in the center and light on the edges, which in turn creates a non-uniform spray pattern across the spray swath. Using spray formulations which are abrasive, such as wettable powder products, will also increase wear rate, along with using higher pressures. Zooming out a bit, there are plenty of options for how spray gets from the inside of the boom to the nozzle tip. The nozzle body is the main connection here, serving as the junction between the boom lines, check valve, and nozzle. There are both wet and dry nozzle bodies, corresponding to whether the spray flows through rigid booms or hosing affixed to the boom structure, respectively. There are also various configurations of multi-nozzle bodies, such as turrets and inline stacks, allowing for rapid infield nozzle changes and, in some cases, controllable simultaneous multi-nozzle flow. The check valve is mounted to the nozzle body and controls flow to the nozzle. Traditional check valves use spring-loaded diaphragms, while pneumatic and electrically actuated variants are also available. Regardless of type, the purpose of the check valve is to aid in clean spray shutoff and the prevention of spray running out of the booms through the nozzles when the spray valve is off. The nozzle cap is the connection point between the tip and nozzle body. These are typically quarter-turn quick caps. Some nozzles are available as single-piece tip and cap combinations for convenience. Check valves can be a significant source of pressure loss. This is important since we measure pressure upstream of the check valve, but actually only care about pressure downstream of the check valve at the nozzle. Manufacturers provide estimated pressure drops for rated flow rates of their check valves, and this can be used to help calculate the expected nozzle pressure. Consider this example. You have 5 psi check valves on your sprayer. Your boom pressure gauge reads 40 psi. How much pressure is at the nozzle? Well, if 5 psi is lost through the check valve, our nozzle pressure will be 5 psi less than the boom pressure. Thus, 40 minus 5 equals 35 psi. While this is a good way to estimate nozzle pressure, it's still preferred to perform an actual flow check for several nozzles on the boom to ensure desired output. Drift reduction adjuvants are spray modifiers, or products that we add to the spray solution to alter the physical characteristics of the spray. Polymers are a class of drift reduction adjuvants that are essentially thickeners. They increase the viscosity and dynamic surface tension of the fluid in an attempt to hold together the fluid flow as it exits the orifice. In general, these tend to shift the entire droplet spectrum upward, making all droplets larger, even those that would already have been large to begin with. While this will certainly reduce drift, coverage may be compromised. What we really want is to reduce the formation of driftable fines without changing the rest of the droplet spectrum. Invert emulsions and oil-based adjuvants produce less significant results than polymers in reducing fines. However, they do narrow up the droplet spectrum by more or less leaving alone the larger droplets. A narrower droplet spectrum is always more desirable, as it keeps the majority of our spray volume in droplets close to our target VMD for a given application. In the end, though, the best adjuvant is not a substitute for proper nozzle selection. A single adjuvant will also perform better or worse for different nozzle technologies, so it's always important to test each combination. Consider this experiment, comparing several adjuvants using both a turbo and turbo air induction nozzle. This chart shows the relative risk of drift for each nozzle adjuvant combination. The dark blue bar represents a spray solution with no adjuvant. The other colors are various drift reduction adjuvants on the market today. Looking at the turbo nozzle first, notice that every adjuvant reduced the risk of drift by reducing the percent less than 150. The gray bar, which is an adjuvant called control, reduced drift the best. Looking now at the turbo air induction nozzle, the risk of drift is already so low that it's difficult for an adjuvant to make much of an impact. However, the light blue bar, an adjuvant named array, actually made drift worse. Overall here though, between these nozzles, we see that choosing the right nozzle has a bigger impact than just choosing a drift reduction adjuvant. Now let's look at the same experiment, but focus on VMD, or the median droplet size instead. Looking first at the turbo nozzle, we see that all the adjuvants increase the VMD except for interlock in orange. Also, we see that control, the product which did the best at reducing drift, also nearly doubled our VMD. That's because control, in addition to array and border, is a polymer and shifts the entire droplet spectrum upward. Interlock, on the other hand, shows barely any change in VMD, but as we saw on the last slide, still reduce drift. This behavior of reducing drift while maintaining droplet size indicates that this adjuvant could be a good choice for the turbo nozzle. Looking at the turbo air induction nozzle now, we see a similar effect as with the turbo nozzle. However, the turbo air induction nozzle produces a very large droplet spectrum without any adjuvants. Using polymer adjuvants with this nozzle makes droplets so large that it will be difficult to achieve proper coverage of the target. As you can imagine, maintaining application rate across an area is critical to a uniform pesticide application. A rate controller is a simple computer which allows just that. The applicator inputs the target GPA and swath width. Using sensors on the sprayer, travel speed and flow rate are monitored. Pressure sensors are typically included as well, but do nothing to affect rate control. During speed changes of the sprayer, a rate controller maintains application rate uniformity across the field by adjusting flow rate. If the number and size of nozzles are unchanged, a higher flow rate will generate increased pressure. As we've discussed earlier, higher pressure creates smaller droplets and effectively more drift potential. The bottom line is that rate controllers help us do a better job by making up for small variations in speed, but can create drift issues if operated much faster than its calibrated travel speed. For sprayers equipped with rate controllers, speeding up during an application will increase GPM to keep GPA constant. Since every nozzle has a recommended GPM range, we need to ensure that our rate controller is not pushing the GPM outside these limits. We can rearrange terms in our GPM-GPA equation to solve for speed. Specifically, if we plug in the maximum nozzle flow rate into the right side of the equation, we'll get the maximum travel speed on the left. Let's look at a related example problem. You are making a 10 GPA application with a sprayer equipped with an automatic rate controller and nozzles spaced 20 inches apart. The maximum pressure for the nozzles is 100 psi, and at this pressure, they have a flow rate of 0.47 GPM. What's the maximum speed you can travel at during this application? Since we're trying to solve for maximum travel speed, we can use the equation we just looked at and plug in the given maximum nozzle flow rate, the application rate, and the nozzle spacing. Crunching the numbers will give us 14 miles per hour. Being our maximum travel speed, traveling any faster would require our nozzles to be operated beyond their rated maximum flow rate and pressure. Technology's response to the drawbacks of traditional rate controllers is pulse width modulation, or PWM. This is a generic term for using electrically actuated solenoid valves in conjunction with an electronic controller to quickly cycle nozzles on and off at a set frequency. While the frequency of pulses is constant, typically 10 to 15 Hz depending on the brand, PWM can alter nozzle flow rate by adjusting the ratio of on time to off time during each pulse cycle. This is referred to as the duty cycle and is typically used as a percent, where 0% is off and 100% is always on. The big concept of PWM and why it's such a useful tool is that using duty cycle to adjust flow rate will not cause a change in pressure, and therefore not cause a change in droplet size. Many newer sprayers use PWM-based rate controllers for this reason. Additionally, being able to control flow on every individual nozzle opens the door to a world of possibilities. One example of what can be done with PWM is turn compensation. When making turns while spraying, the nozzles on the outboard side of the turn need to put out much more flow since they're moving faster, whereas the nozzles on the inboard side of the turn need to put out much less flow because they're moving slower. PWM also enables some types of variable rate technology, where a field can be treated unevenly based on a prescription map. Up to this point, we haven't discussed the impact of the physical properties of a spray solution. Calibration and flow rate information for water is listed in nozzle catalogs, but when switching the carrier from water to a fertilizer, adjustments must be made to compensate for the different spray solution properties. One property is the density, or weight per unit volume. In the US, density is measured in pounds per gallon. The standard density of water is 8.34 pounds per gallon and is used for a reference for other measurements such as specific gravity. A solution with a higher density than water will result in a lower flow rate at the same pressure. Since fertilizer solutions have a higher density than water, sprayers must be calibrated to compensate for the decreased flow. This is usually done by applying conversion factors given in the nozzle catalog to use a slightly higher pressure or larger nozzle. Viscosity is another property that affects nozzle flow rate. It's a measure of friction within the liquid and can also be thought of as a fluid's internal resistance to flow. Some suspension fertilizers increase viscosity enough to reduce flow over 10% compared with water. The effects of viscosity can be compensated to some degree in the same way as density, though it may be necessary to slightly dilute the solution with water to get proper flow. Let's look at an example problem which takes density into consideration. You're making an application of a 4-EC herbicide at 2 quarts per acre and 120 pounds of nitrogen per acre. You're using a 28% nitrogen solution with a density of 10.65 pounds per gallon. Your sprayer has a 1,200 gallon tank. How much 28% nitrogen solution do you need for a full tank? If you're feeling confident in your calibration math, pause here and try this one on your own. You can skip to the end to see if you came up with the correct answer. The first thing to realize here is that this is a well-disguised active ingredient problem. We want to apply 120 pounds of nitrogen per acre, but we are doing so using a 28% nitrogen carrier solution. So, like any other active ingredient problem, we need to convert the active ingredient rate, in this case the nitrogen rate, to a product rate. Since we're given the percent active ingredient by weight, i.e. 28%, we can use the dry AI to product rate conversion formula from our equation sheet. Plugging in our given AI rate of 120 pounds of AI per acre and our 28% AI, we take 120 multiplied by 100 and then divide by 28 to get 428.6 pounds of product, in this case our nitrogen solution, per acre. We eventually need to find the gallons of nitrogen solution per tank, so it's necessary to convert the pounds per acre rate that we just found into a gallons per acre rate. To do this, we must know the density of the solution. The problem statement provided this as 10.65 pounds per gallon. Dividing 428.6 by 10.65 gives us a nitrogen solution rate of 40.2 gallons per acre. As an alternative to the steps shown thus far, it can be handy to remember the nitrogen densities of common fertilizer solutions, like 28% and 32%. The nitrogen density of a 28% nitrogen solution is 2.982 pounds of nitrogen per gallon of solution. If we take the required nitrogen rate and divide it by the nitrogen density of the solution we intend to use, we'll get the required GPA application rate in one step. Our end goal in this problem is to determine the amount of 28% nitrogen solution per tank. However, the rates we're given are on a per acre basis, so we need to figure out how many acres our tank can treat. To do that, we'll need to find the total application rate, including the herbicide. We were given a herbicide rate of 2 quarts per acre, which we can convert to half a gallon per acre. The total application rate is simply the sum of the 28% solution rate, 40.2 GPA, and the herbicide rate, half a gallon per acre. Again, this total application rate is required to determine how many acres a single tank can treat. Dividing our tank size of 1,200 gallons by the total application rate of 40.7 GPA, we find that one tank will treat 29.5 acres. This allows us to reframe the original question. Instead of finding the gallons of 28% nitrogen solution per tank, we can find the gallons of 28% nitrogen solution per 29.5 acres. To do this, we multiply that 29.5 acres by the application rate of the 28% nitrogen solution, 40.2 gallons per acre, to find the total amount of nitrogen solution per tank to be 1,185.9 gallons.